So let's take a look at 8.6. So you may scratch your head and say 8.6, we're in chapter 4. But this material previously was in chapter 4, and 8.6 deals with numerical methods to find area underneath a curve. Um, we looked at using antiderivatives. If we had some function and we wanted to get the area on an interval from that function to the x-axis, we did a Riemann sum where we added the function times the width at each x sub I, and we did n of those, and we let the number of those go to infinity. And then we saw that that was equivalent to doing an antiderivative from the left side to the right side of our function dx. Well, that's all good and well as long as our function is something that we can get an antiderivative for. If our function is something that we don't know how to integrate, then how are we going to do that? So what we're going to look at is what are ways to estimate this area if we're not able to use the fundamental theorem of calculus. If we're not able to get the antiderivative and plug in the right side, plug in the left side, and subtract. So it turns out that using rectangles are okay, but rectangles we saw tended to have a good amount of error. If we broke this region into 4 rectangles and did either a left-handed or a right-handed sum, we would either not include all the area or we would include too much, and it wasn't a great approximation. So one method we can use to make a better approximations is to connect the left and the right endpoints on each interval with straight lines. And what each one of those shapes are is a trapezoid. If we look at here, we just have a trapezoid where this is one base and this is another base. And this distance here is the height. And it turns out that the area of a trapezoid is the average of the bases times the height. If it were just a rectangle, it would be length times the width, but since these lengths aren't the same, we essentially average them, add those together, divide by 2, and that'll give us the average length times that width. So we would just add each of those together. And we'll kind of make a long story short. This y value is going to get used twice because this is a base of the first trapezoid. This is also a base in the second trapezoid. Same thing here. This side is a base in the second trapezoid. It's also a base in the third trapezoid. This side is a base in the third trapezoid. It's also a base in the fourth trapezoid. But this side only gets used once, and that side only gets used once. So we're just essentially going to add all of those together. And the formula that we're going to use to approximate that area is b minus a over 2n times the function at the left side plus twice the function at the next x value. So if that's the next x value, that's the left side. So twice this value, twice the next x value, twice the next x value, and then the last x value only gets used once. And since we're doing 4 trapezoids, in this case, n would be 4. So the b minus a over 2, or let me see, the 2 comes from the fact that we're doing the base and the base, and we're dividing it by 2. So that comes from adding those y values, dividing by 2. The b minus a over n, that's delta x. So that's the height of the trapezoid, or that's the height. The 2 comes from here, and these are just the bases added together. If we were doing that, if we were to add all of these together, they would have some common elements. If the delta x is the same for each of those, then the height would be the same. We would have a 2 for all of them, so we would factor out the delta x and the 2. That's what this is. And then we would be adding the bases that we need for those. So the first trapezoid would be this y value and this y value, which is that and that. This one would be this y value and this one, so that takes care of the other one here and one of those. So this y value is twice, this one's twice, this one is twice. That's why we doubled all the interior y values. So that's all I'm going to say about that formula. What we really need to know is how to use it. So let's look at an example. If we want to estimate the area from 0 to 2 of x cubed dx, that's something that we can get the exact value for. We can just do the antiderivative and evaluate that from 0 to 2. If we plug a 2 in, we get 2 to the 4th over 4, and if we plug a 0 in, we get 0 over 4. So we end up getting 4 to be that exact area. Now, we normally wouldn't do one, or we might not use the trapezoidal rule for this particular problem, because this is one that we are able to get the antiderivative for. Where the trapezoidal rule is really handy is when we have one that we're not able to get the antiderivative for. But before we do one of those, let's practice that on one that we are able to get the antiderivative. So if we want to approximate the area using the trapezoidal rule, let's do it using n equals 4. So we need to do a couple things. If we're doing n equals 4, we need to get our delta x so that we'll know how to break up our number line. We know we're going from 0 to 2, but if we're breaking it up into 4 equal pieces, we need to know what our subintervals are. So b minus a over n. So our delta x is 0.5, 0.51, 1.52. That breaks up our interval into 4 equal segments. So to get our area approximation using the trapezoidal rule, it's b minus a over 2 times n, and then it's going to be f at the left side, twice f at the next x value, twice f at the next x, twice f at the next one, and then this one on the right side, that base doesn't get used twice, so we just do that one once. And then we just simplify this. So we're going to get a 2 on top. That 2 will cancel with that 2. So that out front simplifies to 1/4. And then we just need to plug each of these numbers in. If we plug a 0 into our function, 0 cubed is 0. If we plug a 0.5 into our function, we have 0.5 to the 3rd. And then we're going to double that. So we get 0.25. If we plug a 1 in, 1 cubed is 1 times 2. If we plug in a 1.5, we have 1.5 cubed, and that gets times 2, so 6.75. And then if we plug a 2 in, 2 to the third is 8. So our approximation using the trapezoidal rule will be whatever we get for this. So on the inside we have 0 plus 0.25 plus 2 plus 6.75 plus 8. So that is 17 on the inside. And then times 1/4 or divided by 4. So about 4.25 is what our approximation is, which we know the exact area was 4. So using the trapezoidal rule, we're close to that. We're just off a little bit, and that's not a bad approximation. Just like doing rectangles, we could increase in the number of trapezoids and get a better approximation. But we won't do it with more. But one thing about the trapezoidal rule is it doesn't take nearly as many subintervals to get a good approximation as it does rectangles, because doing straight lines between the endpoints, we have a lot smaller gaps than we would if we were doing rectangles. So that's doing the trapezoidal rule. Simpson's rule is very similar to that. We just have a slightly different formula. Approximating the area using Simpson's rule, it's b minus a over 3n, the function at the left side, plus 4 times the function at the next x value, twice the function at the next one, 4 times, that's not a 4, that's an f, 4 times the function at the next one, 2 at the next one, and then whatever the last one is just gets counted once. So instead of having 1 here, and then all the middle ones having a coefficient of 2, we alternate between 4 and 2, 4, 2, 4, 2, etc. Also, instead of having b minus a over 2n, we have b minus a over 3n. So if we want to do that same one we were just doing, let's approximate it using Simpson's rule, and again using n equals 4. Now, quick note, Simpson's rule, this is not something you have to know in order to know how to use it, but if we have some function, what Simpson's rule does is instead of using trapezoids or rectangles, it actually uses quadratic functions, which are parabolas. So when it breaks our interval up, it uses the area under this parabola, the area under that parabola, the area under that parabola, and the area under that parabola. That's a curve instead of a straight line, so often that parabola generated between here and here being a curve is going to approximate that function better than a straight line would. So often Simpson's rule is going to be the best approximation. So let's use the formula here and see what we get. So our area approximation using Simpson's rule is b minus a over 3, and we're just going to do 4 subintervals times f of 0 plus 4 times f at 0.5, 2 times f at 1, 4 times f at 1.5, and then we're to the right edge of the interval, so that one just gets used once. So these are the same x's that we used when we were doing the trapezoidal rule. That's because we were doing 0 to 2 still, and we're still doing 4 subintervals. So our delta x was still 0.5, so we go over 0.5, go over another 0.5, and those are the x values that break up our subintervals. So now we just need to evaluate this. So we have a 2 on top, We can reduce that 2 with that 4 if we want to, or we can just call that 2 over 12. And remember, this is our function. So if we plug a 0 into our function, we get 0. If we plug a 0.5 into our function, so 0.5 cubed, this time we're multiplying that times 4. If we plug a 1 into our function, we get 1 times 2. And then we do 1.5 cubed. That one gets multiplied times 4, so 13.5. And then we plug a 2 in, and we still get 8 for that. So we could reduce out front and call that one 6 if we want to. If we add these together, we have 0.5 plus 2 plus 13.5 plus 8. That's 24. If we divide 24 by 6, we get 4. That's actually the exact area. That's the same thing we got when we did our area using the fundamental theorem of calculus. It's not always going to be the case, but sometimes our area approximation, we use Simpson's rule, is going to match the exact, because again, it's a curve. So curves are going to follow polynomials much better than straight lines would. So it's just a matter about how we use the formula. We use our delta x, which comes from our n. Remember, delta x, b minus a over n. That'll tell us how wide our intervals are. And that'll allow us to break up our number line that goes from the left side to the right side into subintervals. And then for the trapezoidal rule, it's the first x value plugged into the function, and then all of these x is plugged in, and then the answer doubled. For Simpson's rule, when we plug all of these in, we take the answer times 4, the answer times 2, the answer times 4, and we alternate it until we get to the last one. When we get to the last one, we only use that one once. We only use the first one once.